Under basic conditions, something else happens. Rather than first protonating and then continuing on, all we do is really what amounts to an SN2-like reaction in the first place. Once again, we should always draw out reagents over the arrow in good Lewis structure form, so you see that that is hydroxide, and then THF is tetrahydrofuran, which looks like that. Alright, so if we have this nucleophile and we have this electrophile sitting around, there's really only one mechanism that can happen here, and the driving force is essentially that we can relieve strain. This epoxide can be opened only because this will relieve the strain. Oxygen ordinarily, O- is a terrible leaving group, but since this is a highly strained thing, it is much easier to open this up. And of course, this won't happen on its own. It needs an incentive. So really, this is an SN2-like mechanism where hydroxide comes by and opens the epoxide. So these set of two arrows really are the only possible outcome. There's a choice, again, between an attack on a tertiary position and a secondary position. This, since it is an SN2 reaction, really will go via the SN2 mechanism. And what I mean by that is you're going to attack the less hindered side always. So the result is simply opening of the epoxide from the bottom. So the stereochemistry is going to invert, and the hydroxide did the attack, so OH ends up coming in from the back. However, the electrons are now kicked out onto the oxygen on top, so that is O-, and there is a methyl sitting back behind. Again, this is a simple SN2-like mechanism. The only reason why this happens, though, is because you're relieving strain on the epoxide, and that's what causes this to go. Otherwise, O- is not a good enough leaving group. So this attacks, opens the epoxide, that is the result. This is not the final product because you would always do some form of acidic quench in the lab, so you don't try to isolate this material, you simply dump in a little bit of acid and some water as a means of quenching. And then you do a separation. You take this material, you shake it up in a separatory funnel with your solvent, THF, some water, do some more extractions, do a brine wash, dry over sodium sulfate. All of that is what comes into the general acidic quench. Ordinarily, we don't specify what the acid is. We just say, hey, H plus and H2O, a mild sulfuric acid or mild concentration of any acid really will do it. It doesn't matter. As long as you have some acid and water, the end result is that you end up isolating the diol species, and what you now have is you've opened the epoxide from the back, so the two oxygens end up anti to each other. The new oxygen is the one that was the hydroxide. The old oxygen is the one that remains up. The methyl is unaffected because it was uninvolved in the reaction. This is the final product that you isolate, again, after an acidic quench. So you really want to think of this as being first attack of hydroxide in the presence of THF, and then to quench. I bring this up in part because we're now going to be dealing with the idea of quenching in several other reactions we're going to use. And there's a larger point to be made here about how this epoxide will react in general with a lot of organometallic reagents. So that's where I'm going to go next. We're going to take this epoxide and react it with a bunch of organometallic reagents, reagents that have both organic side and a metal side, and they will all work essentially the same way. We're going to open the epoxide from the bottom. And so let me go ahead and illustrate that briefly by saying all of the following reactions that we're going to talk about involve addition of some nucleophile, and the result is going to be that the nucleophile ends up bound at this position for all of the reactions that we're about to discuss. So organometallic reactions just work that way.